Hello mathematicians, we're going to have a look at the product rule. Now, the product rule is another of these rules which will let us cope with expressions which are more complicated than our simple rule will deal with easily. So the product rule is written for cases where y is a product of two terms, two factors, each of which are themselves functions of x. So if y equals u of x times v of x, then on your data sheet it gives you dy dx, so the slope of the curve, therefore the slope of the tangent, blah blah, equals u dv dx plus v du dx. Some people like to use this formula really pedantically, and again I'll show you how to do it that way, and then I'll show you the way that I'd prefer you to do it, and which I personally think is easier, but it does require that you pay attention to it. So if we look at this here, y equals x plus 1 times x squared minus 2. Now one of these is then going to be u, which is a function of x, and one of them is going to be v. And it doesn't matter which you think of as u or v. So if we do that, then when we look at our formula here, dy dx is going to require us to work out at some point du dx and dv dx. So the people who use this formula, once they identify u and v, so u equals x plus 1, v equals, in this case, x squared minus 2, then du dx, they would say, is equal to the differential of this, which is 1, and dv dx is the differential of this, which is 2x. Therefore, dy dx equals u, which is x plus 1, multiplied by dv dx, so that's 2x, plus v, which is x squared minus 2, times du dx, which is 1. So we get to this point, and then after that, probably do some tidying up if the algebra is relatively simple. So we can see, for example, that if we multiplied 2x into that, we'd get 2x squared plus 2x plus x squared minus 2, and then that simplifies to 3x squared plus 2x minus 2. Now there's no need to go ahead and try to factorize that or anything. It's just a matter of simplifying, tidying it up really. So that's the use of the formula, and it's also a fairly common setting out for people who use the formula. Now there is some evidence that people who use this formula do well when they do it, but I think it's just because it makes them slow down and pay attention to what they're doing. However, slowing down comes at obviously a cost in time terms. So I'm going to talk to it differently. I'll just change the pen color first. And so I actually prefer to have a conversation in my head when I'm doing it. I know it's a little bit dangerous. They might take you off in a padded wagon, but nobody else hears what's going on in your head. So, to my mind, the key thing is recognizing that you actually do have a product, because we'll see later on we have other options. So a product is just two things multiplied together. So that's that thing and that thing. And they'll be in some sort of order, and there will only be two of them, because it's a product of two functions. So I do this by saying in my head, therefore dy dx is, put down the first. So I literally write that, multiplied by the differential of the second. So that's multiplied by 2x, plus put down the second and multiply it by the differential of the first. So I get to this line without all of this set up. And then from here, it follows on exactly the same way. So it's just, as I said, having that conversation in your head, identifying the two parts, And then even in any order, put down one, multiply it by the differential of the other, plus put down the other, multiply it by the differential of the remaining one. And I'm sure that's something that you can master without any worries, and it's how I'll talk about it in class. So let's have a look at these examples down here. Now these examples are complicated ones. They're not as straightforward as that because they're actually going to require that we do two rules at once in some cases. So let's have a look at, I'll do a couple of these. So let's look at this first one. If this is what y is, first of all identify what the product is, and it's an x being multiplied by a 3x plus 5 all cubed. Now the 3x plus 5 all cubed is in turn a function of a function. So we have to start looking for the shape of the things that we're differentiating. So when we use multiple rules, it becomes even harder, I think, to do it with the formal setting out. It's more succinct to do it with the process having been arrived at by the internal conversation in your head. So the key thing is that it's a product. So my rule is put down the first, multiply it by the differential of the second. But when I get to differentiate the second, this is now function of a function or chain rule. So it's going to be 5 times 3x plus 5 squared times the differential of what's in here, which is a 3, plus put down the second, which is my 3x plus 5 all cubed again, times the differential of the first, which in this case is nice and easy, it's a 1. So then we start tidying things up. So I can see that I've got 5 3's 15x times 3x squared, times 3x plus 5 all squared. Let's get rid of that again. Plus 3x plus 5 cubed. And it's often the case in these sorts of questions that this then becomes associated with the common factor. So if I took 3x plus 5 all squared out as a common factor, then out of this term, that will leave me with 15x, and out of this term, it will leave me with a 3x plus a 5, which I then subsequently tidy up to get 3x plus 5 all squared times 18x plus 5. Okay, so let's have a look at another one. I'll do this one because I've got no space to do B. So, what are the two things that are being multiplied? Well, it's an x to the 4th being multiplied by a 1 minus 5x to the 6th. So, my rule is put down the first, multiply by the differential of the second, which is a function of a function. So that'll be 6 times 1 minus 5x to the 5th times minus 5, plus put down the second, which is our 1 minus 5x to the 6th, times the differential of the first, which will be 4x cubed. And then look for common factors there. So I can see that there's a 1 minus 5x to the 5th, which will turn up in both of them. So that's one part of our common factor. And there's an x cubed here, and there's an x to the 4th there, so a common factor is x cubed. So all of that is outside of. So I've got minus 30 times x left out of the first one, minus 30x. And out of the second one, I've got a 4, and I've got one lot of 1 minus 5x. So I've got x cubed times 1 minus 5x to the 5th times, if I expand this out, I've got 4 minus 20x and minus 30x, so that's 4 minus 50x altogether. So that's my final answer just there. Our next question is a more typical, even though straightforward, application. So part A says differentiate this function. So if this is y, I won't rewrite it, I would if it was an exam, then y dashed is going to be, I look at it, I notice that I've got a product, so put down the first, multiply it by the differential of the second, so that's 5, 1 minus x to the fourth, times minus 1, plus put down the second, 1 minus x to the fifth, times the differential of the first, 3x squared. Gather or tidy things up so I can see that in this term and this one, 1 minus x to the fourth is a common factor, and there's an x squared that turns up in that, and at least that many in there. I can't do anything with the numbers, so I've got an x squared. Now, in this term then, I've got minus 5 times x left. And over here, in this term, I'm going to have a 3 and a 1 minus x that's left. So again, still tidying up, x squared, 1 minus x to the fourth, and here I've got minus 5x plus 3 minus 3x, so that's plus 3 minus 8x. So there is my differential. Now again, never lose sight of what you've just done. It's not just a mechanical process. You have differentiated so that what you've got is an equation for the slope of the curve anywhere, or the gradient of the curve anywhere, and it's therefore the gradient of the tangent depending on where we locate the tangent on the curve. So when we get to part B, if we've got that in mind, we can have a better chance of figuring out what exactly they want us to do. So it says, hence show that the curve has horizontal tangents at these three spots. So if a curve has a horizontal tangent, so write this stuff down. Horizontal tangent, that implies that y dashed equals 0. The slope of the tangent and the slope of the curve is 0. We simply have to show that the slope is 0 at these three values. So we test them. So when x equals 0, plug that into our expression for the slope, which is y dash. So that equals 0 times 1 minus 0 and 3 minus 0. But the main thing is, we knew as soon as we wrote that first 0 down that y dashed is 0. When we get to x equals 1, y dashed equals 1, minus 1 squared is 1, times our second bracket is 0, and our third bracket is whatever it is, we don't really care. The main thing is that once we've found that that one's 0, that will become 3 minus 8 minus 5 just for completeness, but it's 0. And finally, when x equals 3 on 8, y dashed equals, and I'm going to write this slightly differently, slightly more lazily, but elegantly in a way. So when x equals minus 3, 8, y dashed equals 0, since 3 minus 8x equals 0. So I've put down the reason why. It's one of the three things being multiplied is actually 0. So as you go through these problems, remember that the product rule is just a process for finding the differential. Once you have the differential, it's more important to know why you've got the differential.